Thank you, Satoru. Good morning, ladies and gentlemen. The title of my presentation today is Lighting Electromagnetic Environment from Continuing Current Fields to X-rays. Can you hear me well? Is it okay?
Is it okay?
Yes. All right. As you know, all lighting processes are associated with the motion of electric charge, and therefore can be studied via measurement of the electric and magnetic fields produced by that charge motion. On the one hand, lighting electric and magnetic fields are needed for studying the effects of the coupling of those fields to various circuits and systems. And the induced effects are particularly hazardous for sensitive electronic circuits. On the other hand, measured electric and magnetic fields can be used for estimating various lighting parameters, the lighting location, and for testing lighting models. Those fields can be also used for studying the interaction of lighting with the ionosphere. These slides show the electromagnetic spectrum. There are two scales here. One is frequency F in hertz, and the other one is the wavelength lambda. And of course, the wavelength can be found by simply dividing the speed of light by frequency in hertz. For audio and radio frequencies, it is customary to characterize electromagnetic waves in terms of their frequency. For optical signals and optics, usually the wavelength is used. And for ionizing radiation, usually the energy in electron volts is employed. And to find the energy, we just need to multiply the frequency in hertz by Planck constant. So all three ways to characterize electromagnetic waves are related. There are many different Is it better now? Better?
Better? Okay. Better, okay.
So there are many lighting processes, and some of them, for example, long continuing currents, they are characterized by frequencies of the order of few hertz. So 1 hertz is here, and so few hertz would be the frequency corresponding to long continuing currents. On the other hand, X-rays and gamma radiation, they are associated with frequencies of the order of 10 to the 20th hertz. So this presentation will cover essentially the entire spectrum of electromagnetic waves. This is an outline of my presentation. I start with wideband electric and magnetic fields produced by lightning at very close distances, tens to hundreds of meters. Then we'll talk about wideband electric and magnetic fields produced by lightning at 1 kilometer and beyond, larger distances. Then high frequency and very high frequency radiation produced by various lighting processes. Electric fields in the immediate vicinity of the lighting channel. This means within tens of centimeters to maybe a few meters from the lighting channel. And finally, optical radiation and X-rays produced by lightning will be discussed. Electric and magnetic fields at distances of the order of tens to hundreds of meters are usually measured for rocket-triggered lightning. However, there are some measures for natural lightning as well. What you see here is a still picture of rocket-triggered lightning at Camp Landing, Florida. And you can see about 10 meters of the channel. And in this experiment, the launcher was entirely below ground surface in order to reduce its influence on measured fields. Electric and magnetic fields were measured at 15 and 30 meters. And on the next slide, I'm going to show some electric field and electric field derivative measurements for one of the strokes in this particular flash. Our 4 panels here. The two on the left show electric fields measured at 15 meters and 40 meters from the lighting channel. And the time scale is 100 microseconds in each case. On the right, the two panels show the corresponding electric field derivative B, also at 15 meters and 30 meters. All four waveforms for the same lightning storm. The electric field signature at such close distances, they appear to be kind of V-shaped, with the leading edge of the V being due to leader, the trailing, usually sharper edge, due to the return stroke. And the bottom of the V is the transition from leader to return stroke. The magnitude of electric field change in this case at 15 meters is 100 kV per meter. It's a typical value. If we move to 40 meters, it would be roughly twice smaller. For DEDT signatures, the transition from leader to return stroke corresponds to zero crossing from those leads. So the negative portion of the signature is due to leader, and positive portion due to the return stroke. Most electric field measurements can be used to infer some lightning parameters. And as an example, here we consider an equation for vertical electric field change due to leader, delta EL. And this equation is valid for the case of constant line charge density. And ZT is in this equation with the height of the leader tip above ground surface. Other geometrical parameters in this equation are shown in this sketch. So when the leader extends downward, it deposits charges, usually negative charges on the channel. And in this model, an equal amount of positive charge of opposite polarity is placed as a source in order to satisfy the principle of concentration of charge. For the case of ZT equals 0, that means the tip of the leader is a ground surface, it's a fully developed leader channel, and distances are, as shown here, much smaller than the length of the channel. This is the exact condition that needs to be satisfied. This long equation reduces to this very simple relationship between vertical electric field change, charge density, and horizontal distance between the lightning channel and the observation field. And again, this is vertical field, although the equation resembles the equation for horizontal electric field due to uniformly charged along wire. Anyway, from this equation, if we measure electric field change and we know the distance, we can infer line charge density. And these are some results for measurements at 15 meters and for measurements at 13 meters for the same strokes. Different colors that correspond to different years of observations. And the histograms, they give line charge density for dark leaders in microcoulomb. The mean value is about 100 microcoulomb per meter. This is an easy to remember value. And if you can assume a reasonable value for capacitance per unit length of the channel, you can infer the potential. And for measurements shown here, the electric potential of the leader channel was about 11 megavolts. We also inferred charges associated with individual leader steps for dot step leaders in triggered lightning, also using close field measurements at different distances. And we found that for individual step, the charge involved is a few millicoulombs. So these values, line charge density and step charges, are important, for example, for evaluating the validity of high voltage lab results. And usually leaders in laboratory associated with much smaller charges. So some of the laboratory results are not directly applicable to light. Now moving to larger distances, 1 kilometer and beyond. And I'm going to show first this overall electric field change, vertical electric field change, due to a 4-stroke flash, natural lightning flash, that occurred at a distance of 6.5 kilometers. The time scale is indicated here, 66 milliseconds per division. Vertical scale is also here. This is the entire flash record. And 4 strokes are clearly identifiable. And stroke number 3 here was followed by long continuing current. So long continuing current electric field changes appear as slow ramps of the same polarity